Welcome to Streaming 103, the third and final part of a intro to streaming systems. This time we will cover delivery semantics. So a little bit about me. If you haven't seen the past two, I'll go ahead and tell you a third time, or I'll go ahead and tell you the first time. My name is Josh Fisher. I am a team lead at 1904 Labs here in St. Louis, Missouri. I am an Apache committer and PPMC, or Project Management Committee member on the incubating project Heron. And I wrote a book. The book is called Grokking Streaming Systems. I co-authored it with a person named Ning Wang. We are looking to get this book published hopefully by the end of the year. And that is also the reason why I'm on Manny's channel tonight. So a high-level overview tonight of what we're going to talk about. The main topic is delivery semantics, right? And then we're going to break that down a little bit and understand what accuracy guarantees mean to you in streaming as a developer, and then how to choose that right guarantee. And then from here, being the third part of this talk, where do we go from here? What's the next step? In the second talk, I was talking about a problem we were trying to solve, which was we had a credit card system that was, taking credit card transactions, and we had a fraud detection system that would basically feed off every transaction that came into the system, which is pulled in by the transaction source. It would fan out events, which would mean it would copy out events to each one of those analyzer components you see in the middle. And then at the bottom of the job, it would then aggregate all three of those scores, save them in a fraud database to your right, and then that transaction presenter would present that fraud score to the payment bank to say, hey, you can pay this transaction or not. And I'll go into the details of each of the components here in a minute, but what we didn't talk about is in real life, things go wrong. Things go wrong all the time. And in streaming, how do you guarantee correctness of your jobs, especially when you're working in distributed systems? So to jump into the details of this job, so the transaction source is going to be pulling events out of the API gateway, and then it's going to fan them out to each one of the analyzers. The average ticket analyzer is just going to look for the average ticket that is spent by the cardholder. The windowed proximity analyzer is going to look for large jumps in physical location between physical swipes, as in can John go swipe his card in Illinois and then 5 minutes later go swipe his card physically over in California? It's probably not possible. And then the window count transaction analyzer, that's just going to be looking for a lot of transactions in a certain time window of streaming. If some of these concepts I've talked about so far are kind of unclear, that's maybe a good opportunity for another talk. But for now, we're just going to stick with this. And then finally, at the bottom, we're going to have this score aggregator aggregate all the scores from these analyzer components, persist them in a database, which then the transaction presenter will present the accumulated fraud score to the paying bank to say, hey, you can pay this transaction or not, or pay, hey, you should pay this transaction or not. So when we talk about accuracy or reliability in streaming systems, it can become very, very tricky, right? So if you look here, we have a job with 5 components, and while it may look somewhat simple here in this job, if you think about it in a real life system, these components could be on different physical machines. They could be in different VMs. They could be in many. Most likely they will be. And because of this, transactions or events have to transition from one component to the next over the network. And in real time, this can really cause a lot of problems, because what happens if a component goes down? What happens if a source goes down? How do we replay events that accidentally that aired out because of some network error? How do we make sure things are accurate? Because jobs like fraud detection systems and credit card processing have to be, in my opinion, 1,000% accurate, right? Because nobody wants their card charged twice. So we have an example here to kind of start to show some of the problems that can come on, or that can happen in a job. And for instance, this job particularly is something called a partial result, right? So the transaction source is going to, for this scenario, take 3 transactions, right? We'll call them T1, T2, T3. It just stands for transaction 1, transaction 2, transaction 3. And when that transaction source pulls each one of those events in, it's going to fan out a copy. If you remember correctly, fans out a copy of each transaction or event. In this case, T1 would be replicated 3 times each analyzer. T2 would be replicated 3 times to each analyzer, and T3 would be replicated 3 times to each analyzer. And then finally, those scores, each one of those events would be scored by each analyzer, and then at the bottom, the score aggregator would then aggregate all the scores for T1, T2, and T3, and then it would persist those in the database so that the transaction presenter can say, hey, this has a transaction score, a fraud score of 0 to 3, 0 being probably not fraudulent, 3 being the most fraudulent. But let's say in this instance, the average ticket analyzer is having an issue, right? So the average ticket analyzer is here on the left. Let's say it's fallen behind because of constrained compute resources. It has other things running on the physical machine and they're causing issues that is causing the calculation to fall behind. And because of that, we can say that transaction T2 only had 2 of the 3 analyzer components deliver scores. And because of that, we have a partial result. And then we have an inaccurate result. And because of this, we have this inaccurate fraud score or partial fraud score. This causes more risk for things like banks. And then that should make you think, why would I ever want to do streaming systems, especially in critical systems? Well, we'll get into that. In chapter 5 in this book, we're talking about delivery semantics. And what we do in the scenario is we add in another job into the system, right? So we have the fraud job that's here on the left. We're going to kind of gray that out for now and kind of ignore it. And we're going to add a new job, which is a little bit simpler. We're going to call it the system usage job, right? And so what this thing is going to do is it's going to give a real-time view of usage as a whole to the system. And we're going to kind of fudge some details just so we can get through the learning of this. But the overall goal is just to give a 360 view of how the system's working at any point in time. And accuracy for this job that this arrow is pointing to is an utmost importance, right? So we want this thing to purr like a kitten. There is a loaded term we're going to come across right here, and you're going to hear times delivered versus times processed. And a lot of times these get confused in conversation, right? Because, there's a very fine line between times delivered and times processed. And, they actually have 2 very distinct meanings, but they're very closely on the same line. So their true definitions can really get blurred. So if we look at the steps that happen in the system usage analyzer, right? So let's just look in the details of that one middle component. If you look here, events are going to come into that component, and that component's going to have 4 steps. The first step is this get detection result. And we're going to say that this thing can fail sometimes. And the reason is for whatever reason it fails, and it'll have to be done again. If this happens, let's say we have transaction 2, which I think was causing us problems on the last slide, comes into the system usage analyzer, and it hits this detection result and it fails. We can replay transaction 2 to try it again, right? And let's say transaction 2 fails 3 times on get detection result. And finally, on the 4th time, it is able to get through all 4 of those boxes, which is get detection result, count the fraudulent transactions, count the total transactions, and finally emit the results. Because of this, we can say that this event was delivered one time, because if you think about the system usage analyzer as a black box and you don't look at the details, from the output, the emitted results, the result from the detection result, the fraudulent transactions and the total transactions, they only emitted, all 3 of those steps only emitted results one time. However, that event was processed 4 times because the get detection result failed several times. If you can hear Bernie, I apologize. We'll try and carry it on. So the fine difference between times delivered and times processed is you can process event multiple times with only having a times delivered of 1. And times delivered can kind of be thought of as an illusion. And if you're unclear about why yet, that's okay. We will get into that, a little bit further into the talk. So choosing the right guarantee. This is often sought about or often talked about between streaming professionals. A lot of times when you first come into this, this field, right? So Everybody wants jobs to work the way they're supposed to work the first time. I mean, why else would we build technology? The three most widely supported delivery semantics that I'm going to talk about today, there may be more, is at most once, at least once, and exactly once. And you also may know exactly once as effectively once, and we'll get into the details of that here in a little bit. That's related to times delivered. We'll come back to that. But these are your three top level semantics that you're going to hear about in any job. Now, without getting in, I meant to clean up some of this so it's a little bit easier to read. But in an overview, at most once guarantees you zero accuracy because there's no guarantee that an event will be processed at all. It's saying at most we will process an event one time, at most, which also means 0 times. At least once also does not give a guarantee of accuracy because it's processing all events at least once, which means every event will be processed at least one time, maybe more. All right, so then you get into these duplicated events, and you think, why would I ever get into this? Well, we'll get there. And then finally, there's exactly once. And exactly once is a little bit of a smoke and mirrors, but exactly once is a semantic in which you have accurate results that you can guarantee are correct within streaming jobs and or distributed systems. Well, distributed streaming jobs. So at most once. So if you look at the stream work we created for you, and I shouldn't say we, the stream work that Ning created for everybody to go along with this book. He did a really good job at really making streaming frameworks. He built an agnostic tool for the book that really allows you to get into the details of how something works without getting too confused with technology, right? And so what you're looking at here is, I've covered this in other talks, is you're looking at two connected instances, two connected components of a streaming job. So you have instance one here on the left, we'll call that the transaction source for this job. And the one on the right, we can just say is the system usage analyzer. So this is only a snapshot of 2 of the 3 components in the streaming job. And in between here, you're going to see some queues, which are on the left and the right of something called the dispatcher. And the way information is going to flow through jobs at most once is events will come into a instance, doesn't matter which one, but it's going to come into a instance. The instance is going to do the stuff it's supposed to do, and it's going to push that data out to an outgoing queue. And then we have the event dispatcher that's constantly running that pulls data from the left outgoing queue to push it on to the right incoming queue for the next component. And then finally, this next instance, whether it be a system usage analyzer or something else, is going to pull events off of that queue and then process on. What makes this at most once is that the event dispatcher is blindly moving events from the left to the right. There's no keeping a tally mark of, hey, I've processed this many here. So in a course of failure, there's no way of reconciling anything. It just picks up where it left off and keeps going, which is why at most once means really at most once. Because in the event of any type of failure, the event dispatcher couldn't pick up and say, oh, I messed up on sending these last 5 messages, I'm going to resend them. It just forgets it and keeps going. So now we have at least once. We have the same scenario, right? We have 2 instances. We have an event dispatcher in the middle, and then we have those outgoing and ingoing queues on the left and the right of the event dispatcher. So at least once, the same thing. An event is going to come in from the instance, whatever the instance is, doesn't matter. It's going to do its logic, and it's going to push it to the outgoing queue. The event dispatcher then is going to pull from that outgoing queue and then push that event on to the next component's incoming queue. And then finally, the final instance is going to pull from the incoming queue, do its logic, and move on. The nice thing about at least once is that if any of the events failure to be transferred or processed, the engine or the event dispatcher in our case, well, with some details, it'll replay them from the very beginning of the job. Now the trade-off to this is that it's nice. Well, so there's trade-offs, right? So One, we're guaranteeing that every event is processed at least one time. However, we're also not reconciling now that, hey, we've already processed this event once. We're going to do it again just to make sure. And this really comes into play when you have a distributed job with, say, like multiple sources that are reading from the same source, that are coming from the same source. And because of that, if you have distributed ledgers, they can be complicated. And at least once is kind of the next level up for safety. But it still doesn't offer accuracy, because then you have several events that can be processed more than one time, causing inaccurate results. So how at least once works in one scenario is, and keep in mind this is framework agnostic, is by using acknowledgements, right? So if you look at the job that we've been talking about, the system usage analyzer, it has the transaction source, which just pulls in the pulls in the components, pulls in the events, and then passes them down to the system usage analyzer. What's going to happen though in these acknowledgement jobs is that the transaction source, when it takes an event, it's going to send the event into the job and then mark this transaction somewhere, saying that it's going to keep it in memory, or it's going to write in a ledger somewhere. I'm just trying to stay framework agnostic here, and it's going to hang on to that event until each one of those downstream components tell the acknowledger, hey, I acknowledge that I processed this transaction. And then finally, the acknowledger will say, okay, hey, your bottom two components have processed transaction one, and once it gets once the source gets confirmation from the acknowledger, it'll drop that transaction. If it doesn't get confirmation from the acknowledger after a certain point in time, it'll replay the transaction again blindly, going through the same process. I missed some arrows. So to get into a little more details, and hopefully you all can see my writing, I had a hard time fitting some of this into the screen. So the way this works with handling failures is when the transaction source comes in, it gives the event an event ID, right? So if you can see a little bit here with this little JSON blob here, there's an event ID 101, and basically that transaction source then hangs on to that, and as each downstream component acknowledges event ID 101, once all of the components have been acknowledged, the acknowledger says, once all the components acknowledge that, hey, this event has been processed, the acknowledger tells the transaction source this event is okay to discard, and it throws it away. Again, the problem with this is that if there's ever a failure and a transaction has been processed more than one time, you're going to have inaccurate results. There's also times where, when you're using acknowledgements, that not all components are going to need to acknowledge that they've done something, right? So in this case, let's just change the rules a little bit and say that the usage analyzer doesn't need to acknowledge that it went ahead and wrote data. We can just say that the transaction source took the transaction in and did some system usage analyzing, and then it can just send it to the acknowledger, and the acknowledger can say, hey, the only component that we're worried about, the system usage analyzer, has processed this event, so we can consider this done, and then the transaction source will release this. This can all happen with or without the usage writer successfully writing the event to the database or whatever. And this is a trade-off or a specified decision on this is a specific decision that you're going to have to make while designing streaming systems. Aside from acknowledgements, another thing you can do is you can leverage, another thing you have to do is leverage checkpoints and state, right? And so can I give a brief definition of what checkpoint and state is if you think about it, if you're ever playing a video game, right? And so for starting here on the left, you have time in this top bar here, we have time in real life. And that's all we're going to worry about at the moment. And if you're playing a game and you save it, you're creating a checkpoint. You're creating a snapshot of data that becomes, state in the game, right? You're going to save that. You're going to save that checkpoint somewhere. And then when you open the game and play it again, you're going to retrieve that state that was created from that checkpoint and play from where you left off. And this is fundamentally how streaming systems help you process events reliably. We're looking here, we got checkpointing at least once, checkpointing within at least one scenario. So what's going to happen So what's going to happen if you use checkpointing with at least once is when the transaction source pulls an event in from the API gateway, there's going to be this thing called an event log that you're going to need. You're going to have to reference basically a timestamp, right? And when the transaction source pulls those events off, it's going to checkpoint. It's going to create a checkpoint on the data that is processing every, say, minute or some other specified interval. And that timestamp can also be known as an offset. And this is a very simple system, but let's say your transaction source is reading from more than one ledger. Those offsets come into handy, and that's a whole nother. They come in handy with fault tolerance. And that's a whole nother deal, or a whole nother talk. But the transaction source will use those timestamps as a way to roll back, right? So they're gonna pull data in. They're going to look at the offset, and they're going to write the offset to the checkpoint storage, and then they're going to process, they're going to continue on processing the events. So that if any point in time in failure, the transaction source if the job fails, the job can come back up and read from the most recent checkpoint or offset and start processing events again. Now, finally, we've talked about at least once, we've talked about it most once, which is there's no guarantee your transaction can be processed at all, especially in the case of failures. And then there's at least once, which is the transaction be processed at least one time, but could be many more. Now, I will say that I've talked critically about these, and not that there's anything wrong with them, because most of the time your streaming jobs will work just fine. But you should know that in the event of any type of failure, these delivery semantics are going to save you, or they're going to not work. They're going to work for you, or they're not, right? So delivery semantics really come into play when you have issues in your real-time jobs, and issues are going to happen. But if you ever never had issues, you could probably run. You can run a job that has at most once and be okay as long as you never had an issue. But in the perfect world, this is never going to happen. Now, for this talk, I've used the term exactly once, or at least I introduced that semantic as exactly once. But then I've also mentioned the term effectively once. What's the difference, right? If you look, if you think about times processed versus times delivered, if you think about that, that component we broke down, we showed the multiple steps and how it was possible to try and process an event 4 times, but then finally at the end only have the result as it was processed once, right? That means we're giving the illusion that the event was only processed 1 time, when in fact it was processed 4. It just only had an output of being processed 1 time. And that's where the term effectively once comes from. In my opinion, effectively once is actually more accurate. But when you're coming into streaming systems, it may be misleading to read the term effectively once. Like, what does that really mean? So for the purposes of this book, we chose exactly once. So the key here to effectively once, right? So given the illusion that something has been processed 1 time and only 1 time, is, along with state and checkpointing and all those things that allow for fault tolerance, is idempotent operations. And what I mean by that is an idempotent operation means you can run that operation or that function multiple times with the same parameter, and the same result is going to happen every time, right? So if you look at this top function here called set card balance, it's taking a balance and it's setting the balance. It's setting the value of the past imbalance. So let's say we have a transaction that comes in that sets the balance for $10, and it gets processed 2, 3, 4, 5, 10, even 10 times, maybe 100 times. At the end of the day, the card balance is still going to be $10 because it's an idempotent operation. On the flip side, idempotency is required for effectively once processing, or in other words, exactly once processing. Finally, this transaction here on the bottom, charge is a This is the transaction that's non-idempotent. And so every time you put a value in, it would change the value of the balance. Whether it was 10 times and you say you charge $10 10 times, it would increase the balance, by $100. So let's recap. So you have at most once, you have at least once, and you have exactly once. Or is it effectively once, right? So at most once means a transaction is processed at most one time. At least once means a transaction is processed at least once. And then finally, exactly once gives you the illusion that a transaction is processed effectively one time. So where do we go from here? Well, I'd like for you to check out the Grokking Streaming Systems code base. Ning Wang, my co-author, has done a fantastic job of putting together a framework agnostic library to learn from. It's on GitHub. You can find it here at the link above. He's done a really great job. You can look at our book here, Grokking Streaming Systems, on Manning.com. You can find the URL right above. And that's it. Thank you. So once again, my name's Josh Fisher. You can find me on the socials at joshfisher1108. My email is josh@joshfisher.io. And that's a wrap. Thank you.